So thank you. Thank you for inviting me to speak. Just want to say that everything that I'm going to speak about is the joint work with Nir Avni. So I want to start with a theorem. And here's the point. So let n be greater or equal to 10, and I take the standard quadratic form or positive definite quadratic form on 12 variables. And I localize the ring V, the prime 2. Let's say it doesn't matter so much which prime. And gamma will be spin U of O. So if you don't know what is spin, so it doesn't matter so much for this part of the talk. So the theorem says that for every M, there exists some constant which a priori depends on n. In reality, does not depend on n. Such that if you take the group generated by m powers in gamma, so for example, if m is prime, this is just gamma, then every element of it is actually the product of C m powers. Now, theorems of this form was known for some isotropic groups, certainly for Chevalier groups. But what is special about this group is that this is an anisotropic group. And
can you say something about this group? Because how it's related to this Q? So what is this?
It's spin of Q. I take the spin group with respect to this quadratic form.
Can we think of the orthogonal group at this point?
You can think of orthogonal group. Of this point, later it will be important, but not now.
So this is a form of bounded generation.
This is a form of bounded generation. Now, you can. It's some kind of non-commutative Waring type problems. For example, if m is a prime, then every element is if m is 3, every element in the group is a bounded number of is a product of a bounded number of cubes. So this is a weak version of the theorem that I will say.
I thought you said m is prime.
No, I said if m is prime, then I know that this group is everything. This is the only. If not prime, then it is some congruence subgroup. So this is a nice theorem, but my goal is to convince you that this is an interesting theorem, or at least some generalization of it that connects to important properties of high-rank arithmetic groups. So I want to, the first thing that I want to talk about is the congruence subgroup problem. So I will just fix the notation once and for all. I will use fancy language, but then I will give example, and you can think about this example. It doesn't matter. I just want to state that everything is stated correctly. This is algebraic number field. So S is a finite set of places. which includes all the Archimedean one. O is the ring of S integers. G is an algebraic group defined over O. It's absolutely simple. It's connected and simply connected. And I will assume that this is again it's not so important that the places where that the set of places where GTV is compact. These are just Archimedean places. Again, this is some technical, and it's not so important. And the last thing that I'm going to assume that the S rank of G and the which is just the sum of all the places in S, sorry, not in T, of the KV rank of G is greater or equal to 2. This is definition. So, for example, you can think about G could be, for example, SLNO when when n is greater or equal to 3, let's say, or it can be spin, and again, I write spin and not SO, just I need it to be simply connected of O, let's say Q of O, let's say that the dimension of Q, just to make sure that it's the iron group is greater or equal to 10, and that F contains a finite plane. And then I know that the S rank is greater or equal to 10. Okay, so this is my notation. Every time that I write G O T T O, this is what I mean. Okay. So if we have an ideal I inside O, which is not 0, we have a modulo D reduction map from GO to GO modulo I. And let's call this rho I, this map. And it's turned out because of strong approximation that this map is on 2. But what we care about, is the kernel of this map, of this. And so we denote by G of O of I, just the kernel is the definition of rho I. And this is these things are called principal congruence subgroups. And a congruence subgroup is just every subgroup which contains a principal congruence subgroup. And we say that GO is the congruence subgroup property. Now I'm going to cheat a little bit. It's slightly more complicated than what I okay. I will write something and then I will say something about it. If every finite subgroup of it is a congruence subgroup. So
Every finite quotient.
yeah, finite and finite index, sorry. Finite index subgroup of it is a congruence subgroup. So every finite subgroup contains some group, and in reality, we usually do not want that it really contain this group. It is clear that it contains a finite index subgroup of this group because both of the subgroups are of finite index, or the intersection is of finite index. But what we really want is that to fix the index that every finite index subgroup will contain, let's say, a subgroup of some principal congruence subgroup of index at most 3. Okay, this is what we really want, but let me state it like this. Now, if you see it for the first time, it's look okay. This is some classification of the finite index subgroups, but it turned out that this is one of the most important properties of higher rank groups, at least when it's known. It implies superrigidity. As is stated, it does not imply Margulis normal subgroup theorem, but actually, I think all the proofs that I know of this theorem actually give you another proof of Margulis normal subgroup theorem for the groups where you can show that they have the congruence subgroup property. So, and it has many more consequences. So this is a very important property. So what's known about this property? So Raghunathan of the geo, and I always assume the geo satisfy all these properties, okay? And the geo that if GKV, GK, sorry, is isotropic, then GO has the congruence subgroup property.
I mean, you know, look at the history, you should say Minneker was the first to make any example.
Yeah, I'm taking the final. It's. I don't want to spend too much time about the congruence subgroup property. So what happens in an isotropic arithmetic group? So for example, in some cases it's known. For example, Knetzer proved this. So you take a quadratic form, Q is a quadratic form. And I think that if I remember correctly, the dimension of Q should be greater or equal to 6 or something like this. And then G is spin of Q. And I assume that this is of higher rank, that I do assume that the rank, that the X rank of G is greater or equal to 2. Still assume, then GO has the congruent subgroup property. This was the first example of an isotropic group with the congruent subgroup property.
Can you indicate why an isotropic case is more difficult?
Yeah, so the difference between isotropic groups and anisotropic groups is that you don't have unipotence. And everything becomes easier if you have unipotence. And the main open case for when we don't know nothing is that main open case. Is when G is the norm one element in a finite dimensional division algebra over K. This is the main open cases. So for example, you can take, for example, if this is, you take the Hamilton-Technion, when X, Y, and Z and W belong to Z, let's say 1 over P times Q, when P and Q are distinct primes, then the congruence subgroup property is not known, and this is a major open question. Okay. So the next thing that I want to talk is I want to talk about bounded generation, because this is how people tried to get progress in the congruence subgroup problem in the anisotropic cases. So the next thing is bounded generation.
Your theorem is very interesting because it's, if I'm remembering what you stated as your first theorem, it seems to contradict this recent work of Rapinchuk, etc. They prove that you can't have a boundedly generated set.
You can't, but I will.
Isn't that what you said exists?
No, I said you take the set of all powers. Yeah. I will explain. I explain what's going on. Bounded generation. So a group, by the way, is there a group is said to be boundedly generated, a group gamma, if there exist finitely many elements in gamma such that G is equal to the product, the cyclic subgroup generated by them. Now, I should say that it's always contains information about the full structure of a group. So, for example, if this is a topological group, when I say subgroup generated, I mean the closed subgroup, okay? If it's discrete, it's the discrete subgroup. Okay. So, for example,
But emphasize you're not allowed to switch the order.
what?
You're not allowed to commute it.
You're right. In some sense, you can switch the order because you just will take a bigger scale. You will run overall permutations. The point is that it will be a fixed number.
Okay. I guess you're saying cyclic, so it's G's to powers.
Yes. Yeah.
So I understand. You can look at the group generated by the G1 through G.
No, this is product.
It's important.
No, this is product. It's not a group generated by them, by each one of them separately. Like here I close the group and I multiply it. So it's something like this. Sorry. Like G2, and then I apply it with the cyclic group generated by 3, and then up to GK.
So every element is expressed as G1 to the M1,
Yeah.
G2 to the M2, GK to the MK, in that order.
But then you're allowed to move.
No, you don't allow. You actually want that G will be equal as a set.
Ah.
Yeah. To this. So the first.
So you are saying it's equivalent to the statement that G is the union of these guys over all permutations.
No, not union. No, not union, product. I just said that for example, if you want to, I'm not sure what Peter, what you meant, but I just said that I don't.
G2 times G1.
If you want G2 to G1, so enlarge K to include the permutation, but still you'll get bounded number after all permutation because you are looking at the permutation
The
of
definition is, as he said, every G is of the form G1 to the M1, G2 to the M, so they are integers M1 to Mk, such that every G is of that form.
Okay, so the first example of an interesting group which is boundedly generated was due to Carter and Keller, and they proved that SLN-O is boundedly generated when n is greater or equal to 3. They have a similar result for SL2 when the ring if it's still higher rank, the ring contains unipotent invertible elements. How it relates to the previous question of the congruence subgroup property, it's related in the following way. The theorem of Rapinchuk and also the similar theorem of Lubotsky except the following: GO as the congruence subgroup property if and only it's equivalent to the fact that the finite completion of GO, this is for finite completion, is boundedly generated in the topological sense. So in the topological sense, so you take the closed subgroup generated by these elements.
By the way, to answer Alex's question, and maybe not everybody's familiar with all these things, the Carter-Keller uses elementary matrices.
I will speak about it. I will get back to Peter. And one way to prove that the finite completion is boundedly generated is to prove that the discrete group itself is boundedly generated. So this was a direction that I think for 10 or much more than 10, for a lot of years, people believe.
Just to clarify, in the topological sense, you're looking at the group generated by all these then.
No.
That's
The closure of the cyclic group of generated by G1 times the closure of the cyclic group generated.
Sorry.
I have a silly question. So
Yes.
for anisotropic group, even proving, is it the case that even proving strong approximation is more difficult? Because uniponents, so the proofs of strong approximation that I know, uniponents in a.
Yeah, that's due to Kneser. It's not true.
So it's a slightly different proof.
Yeah, that's why you have to go to the spin double cover.
Okay, so people try to prove that GO is boundedly generated. And as I told you, the interesting case is when GO in anisotropic. Because if it's isotropic, we have other proof of the congruence subgroup property. And then I think last year, for Vaja, Rapinchuk, Ren, and Zanier proved that if they prove a stronger theorem, but I will state it in the form that I want, is that it's suitable for this talk, is anisotropic, then it's not boundedly generated. So in this theorem, the closed direction that people try to pursue.
All right, that uses a very serious number theory.
I will explain it. I will explain. And not the
Just want to make sure that you give credit where it's due.
So this was some surprise because we know that sometimes it's harder to prove things for an isotropic groups, but usually we think that the algebraic structure in some sense is closed, is not so different than the structure of the isotropic cases, and here you have a very sharp difference. So it was really surprising. And let me tell you in two words, in a few words, what is the main difference here? So if A is unipotent, you take a unipotent matrix, and then the entries of the nth power of A is polynomial are polynomial in M. But so if you take now you take unipotent matrix and you start to multiply, you get polynomial equations that you need to solve. However, if it's semi-simple, and if we take an isotropic groups, all the elements are semi-simple, we do not have unipotence, then all the entries are exponential. And it's much harder to solve exponential equation than to solve semi-simple polynomial equations. And so they use the theorem in order to show that you cannot solve this equation, but basically this is what's going on. Okay.
So what goes into that?
Lang's GM. It uses actually the key ingredient is the subspace theorem of Wolfgang Schmidt.
Yeah.
That's quite the finiteness theorem about points on tori generated by finitely generated stuff. Oh, beautiful application.
So now I'm going to speak about conjugacy.
But just to be clear, that shows that the attack to prove the congruence subgroup property for the Hamilton quaternions, for example, cannot go through bounded generation.
Right. Cannot go to
Of the basic group.
This, yeah,
This.
it's not boundedly generated. People used to think it was boundedly generated. This is not true. But he's going to resuscitate it. I think that's where we're going. I mean, people believe
You replace 4 if you replace 4 by 20. That's hard. You had this condition in the first statement that you need.
No, I don't think that.
Oh, it's not only in any division algebra, not just any division algebra which you do, it will be a amazing progress.
Did you also rule out that the profiling completion is not boundedly generated?
No, the profile completion is boundedly generated. This is Lubotsky and Rapitchuk theorem. It must be, but the discrete group is not. It's if there is it's not equivalent, this statement. what is.
No. If the congruent subgroup property is standardly generated.
No, if the congruent subgroup property is true, then the provided completion is boundedly generated. Yeah.
But we don't know. I mean, I'm not so convinced the congruent subgroup property is true for these Hamilton quaternions. I mean, that's debatable.
Okay.
Yeah, I mean,
I don't know. I do not have a new case of the congruent subgroup.
maybe Sarah conjecture that's true, but one can go wrong.
Okay.
Just saying, there's no.
Okay, maybe I should say now we do not know any new case of the congruent subgroup property. So conjugacy with, so I told you that Carter and Keller proved that SLNO is boundedly generated when O is greater or equal to 3. So they have two proofs. I don't know how different they are because I never read the first one. But they have the second proof that they have it joined with a page. So what they prove in this, they can prove. So they use very soft model theory, but it's not really needed. You can avoid and do it completely algebraically, just make life much easier to think about non-standard models. They prove that so let n be greater or equal to 3, then you every element of S, L, and O is a product there exists. Let me write it like this. C and C certainly depends on N. In the work, it also depends on the number field, but it's probably you don't need it with today's techniques, but it doesn't matter for this talk. Every is a product of at most C conjugates of the elementary matrix E1n or its inverse. Okay, so something about how you can express a general element by multiplication of elements in the conjugacy class of E1n or its inverse. For example, this theorem is not true for the polynomial ring over the complex number. This is really a theorem that uses the arithmetic nature of the ring. And so what did I do? How? Why?
Can bring that one up.
Oh, I bring it in.
Reyes tried to solve this problem properly. The analyst runs from 140.
Okay.
It's probably generated.
So, and then there is a theorem of Toslin. That says that the following: let R be a commutative. So let again n be greater or equal to 3. There exists a constant P, which again depends on n, such that for any commutative ring R, and ring is a ring with unit, every element of the conjugacy class of the matrix E1N is a product of at most the elementary matrix. So if you combine these two theorems, if you combine theorem of Carter, Keller, and Page, plus the theorem of Suslin, you get bounded generation. Now, the point that I want to make is that, as I said, Carter and Keller and Page proof really relies on the arithmetic nature of all, whereas Suslin proof does not care about what is all, just care that it's commutative ring. So the arithmetic information is really contained in the proof of Carter, Keller, and Page about conjugacy width, and not in bounded generation. The path to bounded generation is something general that's true for any ring once you have a finite conjugacy width. And from the point of the equation that you get, so if you conjugate a matrix A by a matrix X, and you look at the entries of X as variable, the entries are polynomial in the entries of X. And this does not matter. You can take A to be unipotent, you can take A to be semi-simple, you can take A to be whatever you want. The structure of A is no longer important. And that is why when you pass to an isotropic group, if you look at conjugacy classes and you start to multiply them, there is a much better chance that you will be able to generate anything after a finite number of steps, because you again get polynomial equation and not exponential equation. Okay, but as I told you, the interest in bounded generation, it has some other application besides the congruence subgroup property, but the main interest was to prove the congruent subgroup property. So what about conjugacy width? So we have the following theorem, and again, everything is under the condition that I wrote above. GO as the congruence subgroup property if and only if the finite completion of G let me write the definition before we return to this point. A definition so gamma is a group, and if we have an element in gamma, then the conjugacy width of G is the minimal n, when n could be either a natural number or infinity, such that every element in the conjugacy, in the group generated by the conjugacy class of G, is a product of at most n conjugates of G or its inverse. And we say that gamma is finite conjugacy width, and if every element of it is finite conjugacy width. So the theorem, so let me write it on a new board.
Every element of this class has finite width, but that needs to be uniformly bound.
It needed to be uniformly bounded. So the theorem, the first theorem, is that GO and the congruence subgroup property if and only if its finite completion as finite conjugacy width. So we get a similar situation than the one we had with respect to bounded generation. But in fact, if it has the congruence subgroup property, then you get that there is a uniform bound on the width of conjugacy classes. And of course, if you have a uniform bound, uniform finite, and then of course you have this. So these three conditions are equivalent. So now the question becomes, what conditions on the discrete groups imply that the finite completion has finite conjugacy width? Exactly as was the case with bounded generation. And in bounded generation, we wanted that the discrete group will have finite conjugacy width. So it's not clear what we want in this case, do we want that the discrete groups will have this property, a uniform bound, or just that every conjugacy class will have a finite width? So the one can opt to have a uniform bound, but it's simply not true for anisotropic groups. If GO is anisotropic, there are elements with conjugacy width arbitrarily large. And let me explain, it's not so hard to see it, it's not a deep theorem as in the case of the bounded generation field. What you have, if it's anisotropic, you have a compact place. Let's say you have some place such that it's completion in GR, and you are compact, you have the center of GOPR. This is a finite set. But if you take an element which is really close to the center, since the group is simple, eventually its conjugacy class will generate everything. But since it starts with something that is very close to the center, if you multiply a small number of times, it will stay close to the center. So you take elements which are closer and closer to the center, you get a larger and larger conjugacy widths. So this is not what you are looking for, although I should say that we believe that if you take isotropic groups, you have a uniform bound. It's essentially true for Chebyshev groups, but I believe that it's true for all isotropic groups. This property, we do not know that if the discrete group has this property, then the profinite completion has this property. It's not clear that this property for the discrete group is strong enough in order to imply that the profinite completion has this property. So there is a middle thing between these two things. And here is the conjecture. So the conjecture under the above condition, there exists P such that for every G in GO, the conjugacy width how did I denote the I didn't denote the conjugacy width. Let's the conjugacy. Let's write it. This is conjugacy width of G in GO is at most P times the maximum of the conjugacy width of G, but when you view it as an element of GKV, where V runs all over all places in T, which I remind you places where GKV is compact. So there are fairly many such places, sorry, in S, where GKV is compact. So what?
Would it be about condition?
Excuse me? G is semi-simple, simply connected. Yeah. So what this condition is really said, okay, we know that you might have local obstruction, right? You have in any polynomial equations, you have local obstruction. So if at some real place where the group is compact, the width is very large, then of course the discrete width will be very large. But the theorem says that essentially these are the only obstacles. The conjecture says, or the conjecture says that these are the only. Sorry.
And for the conjugacy with given your local feature.
Yeah.
And so, and then if this conjecture is true, then the congruence subgroup problem.
Yeah. If this conjecture is true, you have the congruence subgroup problem. So this conjecture implies this conjecture implies that G of has a finite conjugacy.
And your point that this condition, unlike the bounded generation, which involved an exponential, is polynomial.
It's polynomial. Yeah.
So that this might be a geometric effect.
So, but so our last theorem,
And this condition is only at the ramified places.
only in the place where the compact places, yeah, and they are real because I
You assume
yeah. So the last theorem that I want to speak about. So G is as before, Q is x1 squared plus x2 squared, and n is greater or equal to 10. O is z1 over f. Now I'm saying a very special case, but this is the case where we dealt, but I'm thinking that everything that I'm going to say is going to be true to any quadratic form as long as the dimension is greater than 10, but we didn't write it, so I don't want to write it on the board, because I'm not sure that we didn't check it. And gamma is spin Q of O. So under the general Riemann hypothesis, the conjecture is true.
Right? Now you've woken everything. Yes, which L functions?
No, it's I don't know. I don't read the well functions, Peter. So what you need from the general Riemann hypothesis is you need some kind of Artin primitive root conjecture, some kind of it, and we used a theorem of Lenstra. So it's very likely. Again, we didn't try it. We are not from that material that if O is enough unit, then you could give an unconditional example, but this is not something that we try to do.
Yeah, because the Artin primitive root conjecture, if you allow enough units, as you know, this is Murthy and Gupta and Heathbrown, becomes true. Yeah, proof.
Yes, so you need it for a general, slightly more than the standard, but again.
What's the upshot? So the upshot is that you are giving a new, so Kneser knows this case the congruent subgroup property? Or not?
Neither know this case for sure. We heavily built on Kneser work. It's not independent. Okay, so there are a few options. One of them is that this conjecture, unlike bounded generation, is true for some anisotropic group, and so maybe it's true for all of them, and maybe you can apply other tools from number theory because you have Diophantine equation in order to try to tackle this conjecture. And the second upshot, which is a direction that I didn't talk about completely in this lecture, is that you see that you can formulate this conjecture. You can actually formulate this conjecture as a congruent subgroup problem, but not on the group itself, but on an unstandard model of the group. And we know that higher end groups in some sense are much more related to the non-standard model than red quadratic group. So this gives you another indication, I don't know if it's strong one or not strong one, to believe that this thing might be true for other higher arithmetic groups. Okay, so this is all I wanted to say.
Any questions?
So is it true that if you have an anisotropic group, that there's always a place where it's compact?
I think that under the condition that I wrote, yes.
I mean, I'm just thinking about the case of like a degree 6 division algebra where the local invariants are kind of order 2 or order 3, but none of order 1.
Can you say?
Yeah, suppose you have a degree 6 division algebra, SL1 of D, and all the local invariants are either, 2 or 3, or of course 0, mod 6.
Okay.
So
so I don't know, but I guess that the conjecture will say that you have a uniform path.
I think there's a theorem of Luster which classifies compact quotient in terms of anisotropy. I think they are really equivalent. So I think we should talk about it. Yeah. Thank you.
There's this groups of probability using bounded generation. Is there any connection between the finite conjugacy with something like property T?
No, we don't know such a connection. As I said, one of the philosophies is to take proof of this that works in the group itself and to generalize them to a non-standard model. Okay, and one of the things that we try to understand, what does property T means for the non-standard model? We do not know what it means, but if you knew some, so they, let's say you take, so your group is G of O, and you take this, and you take G of O star, when G of O star is the ultra power over that principal ultra filter. Okay. So one way to prove that the group is perfect is right because it has, or not perfect as a finite habilitation, it's that it has property T. So if you add some version of property T that works for this group to show that the habilitation is finite in this group, you immediately get that every element is a finite product is a product of a bounded number of commutators, and in some sense you deal with the hardest case of the congruence subgroup problem. So even this will be. So we will really try to understand if there is connected to probability, but we don't know.
You say a little bit about what you need about arithmetic root type conditions to make this work?
Yeah, so we use a pair of length graph. So somebody gives you some. Maybe I do not state it exact, but just slightly many units in such thing. Eta 1 up to it. Okay, this is depend on the number. You get slightly many, and you have another, and you want to find p's where all these units together, let's say P where everything split generates the multiplicative group, but also you want to eat some conjugacy class in the Galois group of this extension. So it's not just one P, but some P in some conjugacy class. So both of conditions together. This is what
You need infinitely many. Or you need to have many primes.
What do you mean?
I mean, art in primitive root tells you 2 is a primitive root modulo P for infinitely many P's. That you just need infinitely many.
You use the infinitely many, but so
With whatever other conditions you want. You want some other conditions and you still want to have arbitrary large primes in your proof.
no, I don't. You need some flexibility with the primes, but in reality, you want infinitely many. I don't know if theory requires it. Yeah.
Oh, maybe it's you need some prime with many, many properties.
Yes, and then you.
Okay, you just need something that does the job for you.
Yeah, but I don't believe that you show that there is one.
I think what James is doing is he's trying to calibrate how close you could get around the Riemann hypothesis. Yeah.
Yeah, so I can tell you exactly what the theorem of Lenstra did. And it's
Right, it's just the case that for the adding primitive root conjecture already, GRH is kind of a very big tool to do when the application of GRH is just something weaker. And so you might hope for one specific problem that, like if you have enough units, you have more flexibility in things.
yeah, so
You can come up with some unconditional.
So people for number theory told us this, and we tried to read the brown paper, and after repainted, we said, okay, we are not the ones that's going to do it unconditionally. Okay.
Any further questions? If not, let's take this.